Hello to everyone. I am Daniel Santana from the National Autonomous University of Mexico. In the last month, we participated in the hack meeting organized by the Mathematical Science Center in Morelia, Michoacan, and we worked on solving or trying to solve this clinical challenge. And I am here to share with you our project results. First, let me highlight the importance of this project, which addresses diseases of high relevance. Diabetes is a global health concern with significant clinical and economic impact. According to the Diabetes Atlas in 2021, there were 500 million of adults with diabetes around the world, with the most of these adults living in a low and middle income countries. That year, nearly 7 million of deaths were related to diabetes. Um, Diabetes is a prevalent metabolic disorder characterized by elevated levels of glucose in the bloodstream due to defects in the insulin secretion or the action of this insulin. Unfortunately, diabetes often leads to severe complications, including cardiovascular diseases, nephropathy, retinopathy, and neuropathy. Now, let me introduce the objectives of this CAMDA challenge. There were two primary goals. The first was to develop predictive analysis trying to identify the risk of developing a disease before its onset. And the second goal is to understand the natural trajectory of these diseases. And this should be done by the study of its progression in these patients. With these objectives in mind, we decided to participate in this challenge. A primary challenge in the biomedical research is the data availability. And to address this, we decided to use two different data sources. The first was the CAMDA's provided database containing nearly 1 million of patients generated from a similar amount of real patients from Andalusia, Spain. And the second database was Diaberia. This is a research database with 136,000 patients from different primary care units from Michoacán, Mexico. Now let's discuss our team's workflow, starting with the data cleaning processes. To illustrate the complex series of electronic medical records, I want to show you this example from Mexico. From Mexico. In a typical visit to the doctor, doctors needs to fill different forms with relevant patient information, which are crucial for medical history. These forms are written in medical natural language, and sometimes it can contain omissions or errors due to time constraints. This human interaction often leads to noisy data that requires to be cleaning. In this cleaning process, decisions are crucial for the results, so we choose to clean the entire database to understand all decisions that were made and to understand the data structure. This data provided by CAMDA was delivered in a JSON format, which helps to store lists and dictionaries in a text format. In this data structure, we detected some common problems such as patients without gender information, diagnoses with multiple age for the same visit, visits without onset age, and visits without diagnosed diseases. After this initial cleaning, we conducted a new processing pipeline trying to ensure data quality. This process excluded about 33,000 patients without diagnosis, 300,000 patients without an age associated with this diabetes onset, 144,000 patients because they have only one visit registered, and the final database contained around 500,000 patients that were divided into four categories based on their health records relative to diabetes diagnosis. During the meeting, we established a work pipeline with three main approaches. The first was topological data analysis exploration, trying to understand the natural history of these diseases. The second was unsupervised machine learning, trying to understand the data's clustering structure. And the third was supervised machine learning, trying to predict the disease before its onset. After this cleaning process, we conducted some initial analysis, including patient journey mapping. In this slide, we summarizes the structure of the available databases, highlighting the prevalence of hypertension and hyperlipidemia as common comorbidities in both databases. We also noted some key differences between the Spanish and Mexican populations. The first is the male to female ratio, um, and the survival horizon for these patients with diabetes, which may reflect differences in social security systems or data biases. Also, we can observe that the CAMDA's database contains some pediatric patients with diabetes, and the Mexican database doesn't contain these patients or this population. Uh, and this means that there are differences in the way that both countries classifies these diseases. In our exploratory data analysis, we can see that most of the patients develop diabetes between 16 and 17 years old. Retinopathy typically occurs between 16 and 18 years old, and cardiopathy and kidney disease are most common between the 17 and 80 years old. Also, we can observe some pediatric patients that develop these diseases uh, that were not expected by the medical team. To understand the patient's journey, we randomly selected one patient and tracked diseases presence throughout the entire life. A key finding was that many patients have several years without relevant health information, and this can make this can make more difficult the prediction of these diseases. In the unsupervised machine learning, we tried various clustering strategies trying to understand this data. The processes involved dimensionality reduction, applying different clustering techniques, and using metrics to select the best approach. In this slide, we can see the result of the database of selected patients used to predict diabetes. We can see two important clusters. In the first cluster, or this first cluster is characterized by hypertensive disease, and the second cluster is characterized by hyperlipidemia, but neither cluster is useful for predicting diabetes. We also performed this evaluation, trying to predict kidney disease and to understand these patients. And we can observe three different groups with the Disney dimensionality reduction. The two most relevant groups differ in the presence of cholesterol-related diseases, but we cannot see significant difference in the predicted kidney disease. In the case of the ischemic heart disease, we followed a similar approach, and we can identify three relevant groups, also in the Disney projection. All three groups are associated with hypertensive disease. The first group presents osteoarthritic disease, and the third group presents hyperlipidemia. More than a half of the patients in all groups have predicted ischemic heart disease. And finally, in this part of the process, in this unsupervised approach, we determined that 20 was the optimal number of clusters for this data set. And using all this information, we conducted a new experiment clustering data based only on disease information. We projected patients into a two-dimensional map using UMAP and performed clustering with the Birch algorithm and 20 groups. And the resulting clusters were evaluated to detect the most common diseases. And this information was validated by Amphora's medical team, concluding that all comorbidities are feasible, but we cannot obtain better predictive capability with these clusterings. Now, for the supervised machine learning, we conducted various experiments to predict diseases before diagnosis. Multiple experiments were performed with and without dimensionality reduction and using different algorithms like Disney, UMAP, and principal components analysis. Using supervector machines, the best results were obtained predicting diseases 5 years before onset with an area under the curve of 0.6. The best prediction was for amputation using a two-dimensional Disney projection with an area under the curve of 0.75. Um, with naive bias, the best results were also obtained predicting 5 years ahead using a nine-dimensional principal components analysis. And the best score was for amputation prediction with a score of 0.71. Um, In the neural networks, we also performed best with 5 years prediction, with amputation prediction achieving the highest score of 0.66. And finally, XGBoost outperformed the other methods, achieving an area under the curve of 86.86 and a sensitivity of 0.9. This optimization process was guided by our medical team, and we focused on reducing the number of false positives. Finally, we conducted further validation using the Diaberia database, training different models with the XGBoost model and trying to enrich this data using the clusters obtained by the previous processes. And finally, this methodology was evaluated on the Diaberia database, and the results were poorer for the evaluation than the training data, suggesting differences between the Mexican and Spanish populations. We also conducted additional experiments beyond these approaches. We explored topological data analysis for data segmentation, achieving better results than the other methods due to the topological data analysis ability to capture geometric characteristics of the data. Uh, Also inspired by topological data analysis, we investigated disease progression, revealing differences between diabetic and non-diabetic patients. However, we found no clear path in disease trajectory, but we also identified some interesting groups of diabetic patients near the non-diabetic patients that warrant further explorations. Also, our medical team researched how our results compare to the scientific literature. Uh, we found several published papers describing attempts to predict diseases, including works by teams from Singapore, Russia, and China. The results achieved scores near or above .8, with study groups ranging from 300 to nearly 4 million of patients. And I want to highlight that a key difference may be the inclusion of different laboratory and demographic data in their studies, but we don't know the complete information that they decided to use. In conclusion, the synthetic CAMDA dataset reveals interesting patient journeys, but needs more validation. Uh, the, these patient journeys needs to be validated. Our clustering and topological data analysis techniques identified subgroups among the diabetics patients that also needs to be validated to be published. Our supervised methods perform well given only diagnosis data, but could be benefit from additional variables such as laboratory values, weight, height, body mass index, and other clinical findings. In the future works, we want to improve the Diaberia database integration as a validation set for this process. We want to invert the training and validation sets, trying to test the transfer learning challenges. And we were proposed to use LSTM neural networks to estimate the most probable next step in the patient trajectories. And finally, I'd like to introduce our clinical challenge team, which includes members from the National Autonomous University of Mexico, the Michoacan University of San Nicolas de Hidalgo, and Amphora Health. And thank you for your attention.